Awesome. All right, so the learning intention for today is exploring how surface area to volume ratio affects absorption. So if you guys remember when we were talking about this assessment task, there is some theory that you need to understand. The first bit of theory is looking at diffusion, more specifically osmosis, and understanding how things absorb into different things, specifically the cell. The second thing you're going to need to understand is surface area to volume ratio. So basically thinking about the outer component of exposure versus the volume inside the cell and why cells are basically small. So those are your two kind of theory components, and both of those theory components you will then use to write up your explanation to what's happening. You're also going to use that theory to help you make predictions and things like that. So just as a reminder, this assessment is a practical investigation, so you will be carrying out experiments. You will be able to carry out the experiment in pairs, but the analysis and write-up needs to happen individually. We have done, or we will do, 2 practices. So the first practice was on the dialysis bags, and that was to help you guys understand osmosis. And now this is our second practice one, and this one's to help you teach you surface area. So, like I said, we were doing 2 practices. This is our second practice one. We will spend this week and probably next week as well, letting you guys have the time to do write-up and giving you feedback as well. Week 3 then is when you guys will be doing your practical assessment and write-up. So again, it's probably going to be about a week or 2 to get it all written up and experiment done. We'll start obviously with the experiment, and then you guys have the write-up component. So let's kind of dive into it. Since we're talking about surface area and volume and the ratio between them, we need to revise how do we calculate volume and how do we calculate surface area. I've given you the equations just to help you guys get started, and I think they are also on the spreadsheet as well. But the main thing we are thinking about is just trying to up and give you guys the answers to the do now, and then we can get started with the material. All right. So in that Mahia question, I asked you to think about a cube. And we're thinking about a cube that has 3 centimeters by 3 centimeters by 3 centimeters. So that's my cube there. If we want to think in 3 dimensions, that's where the cube is going to continue going. Let me fix that. Right, are we okay with that so far? So this is my cube, and I said each cube is going to be 3 centimeters by 3 centimeters by 3 centimeters. So we have length, we have width, and we have height. Gentlemen, thank you. So if I want to calculate volume, volume is equal to the length times the width times the height. Now in this case, it's really nice and easy because everything is 3. So I would be doing 3 times 3 times 3. So let's get the calculator out. 3 times 3 times 3, and I get 27 as my volume. Now we also have to remember units, because if you want to get merit or excellence, you need to have your units there. This would be centimeters cubed. Whenever we're talking about volume, we're thinking about the cubed. Basically think about the fact that you have 1, 2, 3 centimeters that you're multiplying together. Are you okay with that idea so far? All right. The next thing to calculate is surface area. So with surface area, basically you want to find the area of one side of the cube. So we're doing length times width. And then we are multiplying by the number of sides we have. So how many sides do you have in a cube? 6. So we're multiplying it by 6. So in this case, we're doing 3 times 3 times 6. So my surface area in this case is going to be 54, and the units for that is going to be centimeters squared. Cool? Are you all right with that so far? All right. The last step is we're obviously talking about surface area to volume ratio. So basically what you're doing is taking the surface area and dividing it by the volume. So we'd have 54 divided by 27. So the ratio between that is going to be 2.1. And we'll do it to 2 decimal places. Are we okay with that so far in those calculations? I just want to set you guys up for that, so that way you know what you're doing with the practical. Are we good to keep going? All right. So, don't worry, I will scan that and put that online. So like I said, we are thinking about surface area to volume, that we will do a demonstration so you guys can understand the theory to why that surface area to volume ratio is important, and there's some videos so you guys can watch. So we're going to start with the theory first. So that way, when you guys get onto the practical, you'll have a better idea of what you're doing and what to expect. I'll give some instructions on what the practical is, and then we will do the practical. I suspect today, when we think about the success criteria, you guys should be able to explain surface area to volume ratio and how that influences absorption. And I think probably by the end of today, you should have your, well, you're going to have your data for this practical. And that's probably where we're going to end for today's lesson. And then over this week and next week, you guys will be able to do your write-up for it. And again, it's just to give you guys some practice. I can use it as backup evidence, things like that. Are we good so far? All right, keep going. Okay. So let's talk about surface area to volume ratio. So to help us kind of think about that, I want to do a demonstration, so that way you guys know what you're looking for and what we're thinking about theory-wise. So I'm just going to put some gloves on just because that jelly has a lot of chemicals on it. And also, yeah, I just don't want it on me. All right, and then I'll switch to the document camera to show you what we'll be doing for today. This is just to get you guys thinking about the theory of surface area to volume ratio. So what I'm going to do is I'm going to grab some little cubes, and I'm going to cut them up, and I'm putting them on a white piece of paper so you guys can see them really easily. So I want to make 3 cubes that are roughly the same size, and this is, like I said, just to kind of get us thinking about the theory about that surface area to volume ratio. So these are roughly 1 centimeter by 1 centimeter cubes. And I have 3 of them. Are we okay with that so far as ideas? Now, what I want to test out is looking at how surface area is affecting that absorption rate. So I'm going to leave 1 cube untouched, and I'm going to move it into its little beaker, like that. The other one I'm going to cut into some smaller pieces. So I'm going to basically half the size of the cube. So it's basically like 1.5 centimeter cubes. Like that. And I'm going to put all of that into my beaker. Now, why do you think I'm putting all of these pieces into my beaker instead of just 1 piece? That one got away. What variable am I trying to keep the same? Volume. All right, the last one, I'm going to chop really, really fine. So, to nice little cubes. And again, like I said, we're trying to get this idea of surface area to volume ratio. So have I, in all these examples, do I have the same volume? Yes, because I've used the same cubes initially. Do I have the same surface area? No, because I've chopped them differently. Which one has the most surface area, do you think? This one or this one? The one on the left or the right? The right. And that's because I've chopped it up a lot. Yeah? So, what we're gonna do is see that effect of that surface area to volume ratio. So we're gonna put this jelly into some vinegar. So what I have right now with this jelly is phenylalanine, I should say, and that's a pH indicator. So when it's in a basic solution, it is pink. When it's in an acidic solution, it turns colorless. So I'm going to add some vinegar, which is an acid, and we're going to leave it sit, and we're going to see which one turns the fastest. So I'm probably going to put maybe 40 mils. Let's see if that covers them. You guys are going to be doing measurements today. Do I need to put the same amount into each beaker? Yes, because again, it's another control variable. Do I need to put the same concentration of vinegar into all of them? Yes, because again, it's another control variable. And ideally, I should try to get them in rather quickly at the same time, so that way they don't have different soaking times. So that's my big one. That's my medium size. And now we're gonna do my teeny tiny one. There we go. All right. So we're gonna leave that for a little while so we can see the color change. What I might do is show you guys some videos just to give you guys some theory, and we can check on how our pieces are going to change color and which one's gonna be changing color the fastest. Based on your predictions, which one do you think is going to be the fastest changer?
The 8.
The super tiny cut up ones or the big one?
The super tiny.
The super tiny ones. So let's see if that's correct. Like I said, I'll show you guys a little video while we wait for this reaction to occur. Cool. Let's see. All right, here's our first video. Hopefully that's turned on too. Not working.
My job is to make college easier because students have a lot on
Grammarly.
Some organisms are big and some are small, but they're all made up of cells. Some tiny organisms, like bacteria, are made up of a single cell, and all the materials they need must be supplied via their cell membrane. Large organisms, like us humans, are made up of millions of cells. To get the important stuff, like oxygen, to all of the cells that make up our bodies, we have a transport system that takes things to where we need them. We rely on the blood to transport what we need to where we need it. But why are larger organisms made of many cells, rather than a single giant cell? And why do we need such advanced transport systems, rather than simply allowing materials like oxygen to diffuse from the air through our skin to all of our body cells? The problem is surface area. Consider two cubes of different sizes. The smallest cube is 1 centimeter by 1 centimeter by 1 centimeter, and so has faces each with an area of 1 centimeter squared. And there are 6 faces, so it has a total surface area of 6 centimeters squared. The larger cube is 2 centimeters by 2 centimeters by 2 centimeters, so each face is 4 centimeters squared. With 6 faces, it has a total surface area of 24 centimeters squared. So, the larger cube has a larger surface area, but the larger cube also has a larger volume. We need to compare the surface area of each cube with its own volume. The small cube has a volume of 1 by 1 by 1, which is 1 centimeter cubed. It has 6 square centimeters of surface area for every 1 cubic centimeter of volume. We can say that it has a surface area to volume ratio of 6 to 1. If we do the same for the larger cube, we can see that it has a volume of 2 times 2 times 2, which equals 8 centimeters cubed. This ratio of 24 square centimeters of surface area to every 8 cubic centimeters of volume can be simplified to 3 to 1. 6 to 1 is bigger than 3 to 1. It's obvious that the smaller cube has a larger surface area to volume ratio. Let's imagine that these cubes are living cells that need oxygen to survive. For oxygen to spread throughout the cells, it must diffuse through the surface. As the small cell has more surface area relative to its volume, every part of that volume can be supplied with oxygen at a faster rate compared with the larger cell. It would take too long for the center of the larger cell to be supplied with what it needs. If a large organism were made of a single cell, the exchange of materials simply wouldn't happen fast enough. This is what limits the maximum size of a cell. Since our bodies have to be made of many tiny cells, it's important that the materials those cells need are transported directly to them. This is the reason why we have a circulatory system with a really strong pump, that is the heart, constantly shifting nutrients in the blood throughout our body.
Cool. All right. What questions do you guys have after seeing that video? Do you have any questions?
Cells.
What about the cells? Huh? All right, let's have a look at our experiment. So we see the teeny tiny one has gone completely colorless or white, whatever you want to describe it. Can you guys see that? The one in the middle, there's still a little bit of pink, but it's almost completely absorbed. And then the last one, our big cube, hasn't quite absorbed yet all the way through. So we can see here, all of them had the same volume, but they had different surface area. If I can have more surface area to the volume, I'm going to absorb things faster, which is what it's going to limit the size of our cell. Now, the experiment that you guys are going to do is slightly different to the one that I've just done. This is just a demonstration to help get you guys understanding the concept. Actually, I don't think I need both my gloves on because I just want to scoop out the big one. And I'll talk about what you're doing for today's experiment. Where did I put my spoon? Use my spoon. All right, I'm just going to take the big guy out because that can be our example for today's experiment. Cool. And I'll move these guys out of the way because you won't need them. All right. There is a second video, but I won't play it because I want to make sure you guys have enough time to do this experiment. We can always watch it later, but it's just the same sort of theory. What I do want to do is go through the experimental instructions so you guys know what you're doing today. So, on Google Classroom, you guys should hopefully have noticed that I posted the next practical that you guys are doing as a practice. Now, with this practical, we're looking, like I said, at surface area to volume ratio. I've created for each one of you guys a copy of the Google Slides because you each need to do your own report. There's also your own copy of the Google Sheets because you guys are going to need to do your own analysis and averaging and graphing. And then I've also added some SciPad pages because that's going to help with just reinforcing the content. That's actually not part of your assessment. It's just there to give you some extra practice. So, with our surface area to volume ratio, make sure you are writing the name down on who was in your pair. Obviously, I'll know which one's which because you'll each have your own thing to hand in, but it helps me to know who your pair was. And don't forget that I've given you guys the assessment guidelines and what you need to do as an individual versus what you can do as pairs. What you'll notice is different from last time is that we are not giving you as much information. So it's less scaffolded, so that way each time it gets a little bit more difficult and you guys are providing me more evidence. I can use this as backup evidence in case you make a mistake on the actual internal, so do make sure that you're doing and completing this work. I will also be commenting on it and giving you feedback, and you guys have the ability to access this practical and the one we did previously when you are writing up your report on the actual assessment. So please don't resolve any of the comments that I make on there, so that way you guys can have that as a reference when you are doing the actual assessment and you know what you need to fix for next time. The only thing that we're giving you is going to be the method, but we've only given you the method that's up to an achieve level. So if you do want to show me evidence for merit, you can add more detail. All right. So, like I said, we're looking at the surface area to volume ratio. This is the introduction and information for it. The aim has not been provided for you, so you're going to have to write that, and you're going to have to write that based off of what you've read in the introduction and in the task. Same thing, hypothesis, you guys are going to be writing. Now, this is a scaffolded hypothesis. On the actual assessment, that won't be scaffolded. It'll just be completely blank. Just highlight what you think is going to happen. Same thing, this one, like I said, is less scaffolded because we haven't told you what the independent and dependent variables are, and we haven't given you control variables either. What I do want to talk about, though, is the practical, so you guys have an idea of what you're going to be doing. So, with this practical, you are going to be doing 3 repeats. If you want to achieve, if you just do the experiment once, that's enough. But if you want to get merit or excellence, you need to repeat the experiment at least 3 times and do an average, so that way we know that our results are reliable. Now, in this case, what you're going to be testing is the size of different agar cubes. I have the different agar cubes on the side. So there's 3 different sizes you guys are going to be testing. You're going to be testing a 3 centimeter cube, which is this big guy over here. You're going to be testing a 2 centimeter cube, and you're going to be testing a 1 centimeter cube as well. Now, this is obviously a rectangle, because one of the things you guys are going to do for this practical is actually cut them into cube sizes. You guys will be given a metal ruler, so that way you can measure it, and again, that's going to help with that accuracy and that precision if you can cut things properly. So, you're going to be doing 3 centimeter cubes, 2 centimeter cubes, and 1 centimeter cubes. You should be doing 3 of each because you're going to be doing repeats. You will place all of your cubes into one ice cream container, so that way they can all live together with the vinegar soaking in them. With that vinegar, you're going to be adding 950 milliliters, because that'll be enough to cover all of your agar cubes. Are we okay so far? So with this, you're going to put it into our little ice cream container with vinegar. You're going to leave it for 10 minutes, and then you're going to remove all of the blocks that you have in there. And what you're going to do for this experiment is you're going to be measuring how much has been absorbed. So, when we go back to our little document camera, here's the cube that I did earlier. This is the 1 by 1 centimeter one. What you're going to do is you're going to cut your cubes in half, so that way you can see the insides. And you're going to be measuring the leftover color. So you can measure how much has been absorbed. Let me, in fact, open up your Google Sheets so you can see how you're inputting that data. All right. So with the Google Sheets, you have your surface area to volume ratio. So you should be calculating the area for each cube, the volume for each cube. A lot of this will auto-generate because the equations are already in there, so you don't have to worry about doing those equations. What you then do is you want to measure the length of the cube that is not penetrated. So basically what is still pink. So when we go to that document camera and I look at my little cubes, I'm taking my little ruler and I'm measuring how much is still pink after 10 minutes. Why is that not working? Can't see my ruler. Let's restart it. So you are measuring what's the leftover pink bit with the ruler, and then you're going to be able to input that into your table. You have the initial length, and then it's going to be able to calculate then what percentage of the the cube is penetrated with that vinegar. Are you okay so far? Yep. All right. So that's the method. Now this method is to the achieve level. If you want to get this method up to merit, you need to add some more detail to it and make sure you're doing it in blue text so it's very easy for me to see it. Make sure you also take a photograph of it before you add your cubes to the ice cream container with the vinegar. So you should have it laid out on a piece of paper with the ice cream container. Take a picture of it before, so that way you can see what the color of the cubes look like before and what the vinegar looked like before. And then in 10 minutes time, you take another picture and you can see basically how your experiment's changed. So I think you probably will get up to this point today. Well, we're going to need to. And you should be inputting your data for today. Remember, you're doing 3 trials. Then in our next couple of lessons, you guys will be able to do the results. Remember, the averaging and the graphing needs to be done individually. All right, what questions do you guys have for this practical? None? All right, so just some instructions when it comes to what you need to do. You obviously need to stay in your pairs that you had earlier. I'm mindful some people are absent today, so we might need to shuffle around some of the pairs. When it comes to grabbing the different various things that you're going to need, most of it is on that trolley over there. You will need to cut the cubes. So those cubes are a little bit bigger than 3, 2, and 1, so that way you guys can cut them perfectly. You probably will need 3 of the 2 centimeters. 3 of the 3 centimeters, and you probably only need 2 of the 1 centimeters because those ones are smaller and they're easier to kind of cut up. And you can probably get 2 out of 1 block. What else did I want to say about it? When it comes to cutting the cubes, to help keep it nice and tidy, I want you to get a board so that we have a hard surface to cut on, and I want you to put a paper towel, or not paper towel, newspaper over the board so that way it's really easy to clean up. Take the newspaper, crunch it up, put it away. Are we okay with that so far? The boards are right under, I'll show you guys where they are. They're right here. So just grab yourself a board. Like I said, the jellies are over there. There's vinegar over here. There's scalpels. There's these spoons. There's gloves. Because I'm mindful, you guys should be wearing gloves. You don't need to wear goggles for this experiment because we're just using vinegar. Do tie up your hair though. Metal rulers are over here, and then stopwatches over here as well. Remember, you're setting the timer for 10 minutes. What else you guys would need? Oh. And you're going to need these measuring cylinders as well. You're going to be putting 950 milliliters into your ice cream container to make sure it's covered. Cool. All right, you guys ready to get going? You guys remember your progress from earlier? Or do you want me to list up? All right, hop to it. You guys have the rest of the period to get your data.
Don't worry.